So dear participants, as this workshop is based on the modeling and simulation in design and manufacturing, so means you require to do some simulation, and for that simulation you require some models like the voxel models or the FEA models basically. So in this session we will talk how we can prepare the data, basically the parasolid format, in parasolid format or in any voxel or any mesh format for the analysis of human body part. So the topic of this session, or the title of this session, is data preparation for FE analysis of human body parts. So let me first start with the additive manufacturing. As Dr. Tawfiq has told you, that we required some STL file for the 3D printing, and for that this STL file we required to do process in any software like Cura and any other software. There are various software which you can use for the processing and to generate the G or M code. That code further you can supply to the 3D printer in order to print or in order to get the physical model of that particular part. So the very first thing is the solid model. So if you want to print this cube, then you have to generate the solid model of the cube. Now if I will tell you that how you will develop or how you will prepare the solid model of this cube, then most of the participant and everybody can give the answer that we can use the different solid modeling packages like SolidWorks, Unigraphics, AutoCAD, and various other software for to develop the solid model of any object and to convert that object into the STL, so that STL we can use for the code preparation and for 3D printing. But at the same time, for the model preparation of FEA, in the same way we require to prepare some model for the finite element analysis. So if we want to do the analysis on the such piston and such a crankshaft, then we require to develop a CAD model and any solid modeling package, and then CAD model further we can import in the any FEA analysis tool like ANSYS or any other tool, and then we can do the meshing and we can apply the boundary condition, we can do the analysis. So this is a simple process, the normal process which most of us we follow. But question arises, how we can prepare the 3D model. So the simple 3D model like this pyramid we can prepare or we can create in any solid modeling tool like the SolidWorks, ProE, or any other tool. This is where it is very simple. This is also simple. You can create two pyramids and then you can join. This is slightly difficult, but if you know different Boolean operations, then you can also model such a cube or these models. So this is the simple problem, and it is a little bit difficult with the previous example than the previous examples. Like if we want to do some analysis on the gear trains, so first we require to generate the CAD model or to do the designing for these gears, a single gear, and then we can assemble these different gears to do, and this process is known as the assembly, and this assembly we can further import in the any FEA analysis tool like ANSYS, and then do the meshing and then apply boundary condition, and we can easily do any analysis of that. And similarly for this bolt, it is the modeling of this bolt is also quite little bit difficult. But for this cup, if I will tell you to model this cup, then yes, there is some difficulties. There will be, you might face some difficulty to model this handle and this shape because it is not perfectly hemispherical. So in that case, you can use different curves, B-spline curves, Bezier curves to model this cup or such complicated things. And after modeling, you can import these model in the FEA package and do the meshing and do the analysis. You know well how you can do the analysis. But if I will tell you about some difficult models like this model, in this model, if I will tell you how you can generate the solid model of this part, then you might confuse that it is because it is very complicated to do the such kind of solid modeling in the solid modeling, simple solid modeling packages like SolidWorks, ProE, and CATIA. And similarly, this model and this model, these are a little bit difficult to model. So you can answer me that we can do these 3D scanning. If you have a replica, then you can do the 3D scanning, and then after that, these 3D scanning or point cloud data which you will acquire after the 3D scanning, you can transform this data into the solid model or STL file, and that STL file you can use for the 3D printing, and the solid model you can use for the FEM analysis. But when I will tell you to print or the part which is the to print a part, to print any human body part, then the first question arises, how you will develop the CAD model. Because if I will tell you that we require the exact dimensions, then first thing is it is very difficult to measure the dimension of the body part by using the measuring tools like vernier calipers or scales or other tools. So it is very difficult. Then how you will do the solid modeling? And this is the first thing. First thing is the measurement related problem. Another thing, which tools you will use to model the such kind of complicated shapes, so that the STL file we can use for the 3D printing. So we will talk how actually we can develop the solid model or the FEA model of the patient from the patient data for the FEM analysis. Similarly, here you can observe this is the bone or the temporal bone which was processed to form a 3D printed model, which is the exact replica, and this is the back view of the same bone. And similarly, if this is the data of one patient who were having a tumor in the mandible, and then this mandible we want to repair so that the doctor can plan the surgery, or they can create the implant for that patient. So in such a case, you have to model and you have to develop the solid model of exact dimensions of the patient specification. Okay, so such complications are very common when you will go for the patient specific data preparation, either for 3D printing or for the FEA analysis. And here you can see this model was processed, and we have developed the finished mandible bone, and that bone was printed on the FDM based 3D printer, and which this model was used by the doctors to design the implants and to plan the surgery. So let us come to the finite element analysis and the data preparation for the finite element analysis. Basically, the data preparation for the 3D printing or for the finite element analysis from the patient specific data are following initially will follow the same path. So that is why I am telling about the both things. So here this is the part of the backbone, and this is the STL file of the backbone. Then this is the meshed file of the backbone, and this is the after analysis you can see here. So if I will tell you to model the exact backbone in any solid modeling packages, which should have the exact specifications according to the patient bone or the patient data, then it is first question arises that how you will measure the dimension. Okay, because it is already inside the body of the patient. So for this, the first step is the raw data acquisition. So the raw data includes the anatomical data. Anatomical data includes what is the shape of the bone, what the neighbor bone, and the specifications of the neighbor bone also, and blood vessel, is there any blood vessels and any other anatomical complications. So we require to acquire the raw data which should have the anatomical data, exact information of geometry. You should have the exact information of the geometry of any body part which you want to do the model, for which you want to generate the model. And then this data acquisition process should not be painful for the patient. You can do this that first the doctor will operate the patient, then he will remove that particular part, and then you can do the 3D scanning, and that 3D scan data or the cloud point data you can't use for the 3D modeling. It is not the it is not the real practice, and this practice you can't use in the real practice. So for this we can use the X-ray. This is the first solution. We can take X-ray, which will have the anatomical details and the exact information about the size. So this data or X-ray data we can use. But the problem is still, one problem is still there, is that X-ray will have only one-dimensional data. There is not any three-dimensional information. So from this, I should say the two-dimensional data, not one-dimensional. There is only two-dimensional data. So we require the three-dimensional data. So what actually we do? So for that purpose, we can use the CT scan or MRI images. So here you can observe the different slices of CT scan. That slices we can arrange in a particular manner, and then after that we can generate the voxel model from the CT scan data. And here it is. Here you can see magnetic resonance imaging image slice of MRI scan. MRI scan we can also use to prepare the data for finite element analysis and additive manufacturing. So the first thing we require slice data, which we can gather from the CT scanning. So here I am showing you the magnetic resonance imaging image slice of MRI scan. MRI scan we can also use to prepare the data for finite element analysis and additive manufacturing. So the first thing we require slice data, which we can gather from the CT scanning. So here I am showing you the cone beam computed tomography machine. So this cone beam computed tomography machine is basically used to scan the facial data, or we can say the head. If you want to acquire the data of the patient head only, then you can use this cone beam computed tomography. So this cone beam computed tomography will have X-ray source or X-ray projector, and on the other side it will have a detector, and these both things are actually mounted on a rotating beam. This beam will rotate, and here if you will put an object, then this beam will rotate and it will take the several images from the 360 degree, and then after taking these images, the images will further processed, and that can generate a 3D model, or I should say the voxel model of the object in your computer screen. So here you can see the different slices of the CT scanning or CT scanning images. So actually, first thing we have seen the CT scanning, the CBCT scanning process, and then we told you about the from image to model conversion. So first, these different slices will arranged in a software or in any program. Any program you can also use, like MATLAB program, C program, you can write your own program. So these different slices, first you require to arrange in a particular manner, and then after arranging these slices, you will generate a three-dimensional matrix of these images, and then from that three-dimensional matrix we can prepare the side and top view of that body. Here you can observe you will have only the top view, okay? But from the different top views, by arranging the different top views in a stacked form, that will form a 3D matrix, and after slicing that 3D matrix, you can develop or you can generate the side model, side view, or the front view of the body. And then after generating the different view, if you have a little bit knowledge about the human anatomy, then you can do the segmentation of different body parts. Like if you want to segment out the femur bone, then you should know the grayscale value of the femur bone in your X-ray or CT scanning data. So by doing the different, by applying the mask or by doing the segmentation in any software or in any program, you can do the segmentation, and then after segmentation you can generate the voxel model of bone, and then after generating this voxel model we can generate the STL file. Okay, so this is the process. First thing, we require to arrange different slices in a particular way. Then we can generate the front view and side view of the body. Then we can do the segmentation by applying the different house field value, grayscale value, relevant grayscale value to the different body part, and then from that mask we can generate the voxel model, and then after that we can generate the STL file. So this is the process actually how we can generate the STL file from the patient specific data. So once again, the CBCT scan, as you know, and here I am actually telling you the principle of CT scanning, what actually it does. So the CT scanning is actually taking the different the images in this different sliced form of any human body. Okay, this actually taking the images in the sliced manner. Okay, so you will have these different slices of this cross-sectional view. Okay, then that cross-sectional view you require to arrange, as I have told you in the previous slide, to form the front and side view. Okay, so the principle of CT scanning is the CT uses X-ray to generate cross-sectional two-dimensional images of the body. So first you require to generate the two-dimensional images. Then these images are acquired by the rapid rotation of X-ray tube 360 around the patient. So actually this tube will rotate around the patient, as I have already told you, and then that will gather the images. Then that images, then the transmitted radiation is then measured by a ring of sensors. So there will be a ring of sensors that will sense the intensity of the X-ray beam. Okay, on the basis of that intensity, it will define the particular grayscale value for the output images. Okay, so sensors, radiation detectors, and located on the gantry around the patient, and the final image is generated from these measurements utilizing the basic principle that the initial structure of the body can be reconstructed from multiple X-ray projections. So if you will have the multiple X-ray, like if I will tell you to do the 3D modeling of this phone, and if I will supply you only the front view of this phone, then it is quite difficult to you to do the 3D modeling of this phone. But if I will provide you the front view, top view, and side view, then you can easily develop a 3D model. Okay, so in the same way, at the moment when you supply the different slices of same body, then like first slice, image of first slice, image of second slice, image of third slice, then after that, at the moment when you will arrange these different slices in a particular manner, then you can get the 3D model, or you can get the 3D information about this fold. So this is the basic principle of CT scanning. Now here you can observe the working of CT scan machine. So here you can observe, this is the electron gun or the source of X-ray. Then here the X-rays are coming, and here you can see this is the sensor, this is the patient, and the sensor and the projector is rotating actually, and gathering the information in this way. Here you can see, you can observe Here it is the X-ray projector which is rotating around the body, and here you can observe this is the array of sensors which is actually detecting the intensity of X-ray. On the basis of that intensity, that will define the particular grayscale value for that particular image. But the question arises how it will define a particular grayscale value, and how you will know whether it is the bone or it is the blood vessel or muscles and any other thing. So for that you have to understand the CT number. So actually if you will have the 4 objects which will having the different X-ray attenuation coefficient like mu1, mu2, mu3 and mu4. These are the different X-ray attenuation coefficients for the 4 different bodies. Okay, and then here it is the intensity of X-ray which you are projecting on that stack of that 4 objects, and the output intensity of this X-ray is we can denote as I. Okay, and delta X is the thickness of that different 3 bodies. Delta X is the thickness, and that thickness is same, but they are having the different X-ray attenuation coefficient. Then the intensity of this output X-ray, we can then the intensity of output X-ray will be I is equal to I0 this one, and exponential of mu1 plus mu2 plus mu3 plus mu4 multiplied by delta X. Delta X is the thickness of that one body. Okay, so on the basis of this intensity, your sensor or your processor of your CT scan machine will define the grayscale value for that particular pixel. Okay, and here another thing, it is the Hounsfield value. Hounsfield value is the basic parameter for the segmentation of different body parts. So the Hounsfield value is the unit which we can use for this segmentation. And then image reconstruction. So if we can consider this, the situation that a box which is having a hole, okay, and this is the one projection, and a box having a hole, or we can consider a cube which is having a hole, and we are taking the X-ray in the 3 different directions. This is one direction, another, and this is a third direction. So in this case, you can observe these X-ray which are passing through this hole, that will less attenuated, and here you can see a peak. You can observe a peak in the intensity of X-ray, and similarly here these X-ray will attenuated. So here you can see a line equally attenuated, but at this, from these X-ray which are passing from this hole will have the slightly less attenuation, so you can observe a peak, and similarly here you can observe a peak. Okay, so by merging these data you can generate such a model, and by using the many view, such kind of view, you can approximate this exact model. Here you can see a hole or a spot. Okay, so in this way, and when you will use different filtering techniques, then you can get the exact data. So here this is the STL. Here you can see the one slice of the CT scan. Here you can observe different teeth. Okay, and if we want to segment out these teeth, then you can observe that teeth are having the different grayscale value from the soft tissues. If these are the soft tissues and these are the teeth, then it will have a slightly different grayscale value. So by applying the threshold, you can segment it out easily. And so first, so let me tell you about a little bit about the digital image fundamentals. So here it is the image which is having the different pixels. These are the pixel values, so which is the basically grayscale value. On the basis of this grayscale value, we can segment it out the hair and eyes of the Abraham Lincoln. Okay. So what is the optical density? Optical density is that density of this light, which is actually represented in the form of the grayscale value. Contrast is nothing but the optical density, the difference of optical density of foreground and background. So these are the different things, and now let me just tell you about the 3D image representation of 3D image representation. So as I have told you in the previous slides, like when you will have the different images of different views of from the CT scan, then when you will do the stacking of that images, then you will get the such kind of the 3D array, and by slicing of the 3D array you can generate the different views like axial, coronal and sagittal view. So here for the segmentation, here if this is X-ray, or this is an X-ray, and here it is an X-ray of a tooth, then you can observe the different grayscale value for the soft tissues, or I can say for the root canal. Here it is the root canal, you can observe easily, and this is the hard tissue, bone or the hard part of the tooth, which is known as the enamel and dentine. This is the part of dentine, this is the part of enamel, which is the harder than the dentine, so it will having the high contrast. So in this way you can do the segmentation, like you can define the different body parts, and after doing the segmentation you can easily generate the 3D model. So the segmentation, different methods of segmentations are the threshold based, age based, region based, clustering based, and watershed based, ANN based method you can also use. But the threshold based method is more close to the mechanical engineers because it is very simple to understand. So the threshold based method, actually in threshold based method we can define a particular threshold, like the range of the pixel value. On the basis of that particular range of the pixel value, it will generate a mask, or we can say that part of that CT scan we can segment it out on the basis of their pixel value. Okay, in this way. So here I want to segment it out the bone part. Okay, so I have defined the particular threshold value, so that the software is highlighting that pixel which is having that, which are coming under that threshold value. Okay, but still I require to separate out this part. This is actually the machine part. This is the patient body part, and this is the machine, some parts, residual part, some part which is the related to the CT scan machining. So I want to separate out this part so we can use the region growing. Okay, so what is region growing? Yes, is there any question? So what is the region growing? If this is the image which is having the 5 by 5 pixels, and this is your seed pixel, and you are defining a threshold, then this sheet pixel, then your program will search for the neighbor pixel, whether that will come under the threshold value or not. So if that will come under the threshold value, then it will include that pixel. Like here you can see 127 is the seed pixel, it will include that 127. Now it will check for the neighbor pixel. It is not coming with under threshold value, not coming, not coming. Yes, it is coming, so it will include this. Yes, yes, this is also coming, it will include this. This is also coming, this is also coming. So that will include the different neighbor pixel for and grow its region. Okay, so in this way we can segment it out different parts. And after segmentation, after applying the same segmentation for the different slices, we can generate the point cloud data. Here you can see the point cloud data which we have generated using a MATLAB code. Then after that, this is for one slice, for other slices, and by arranging the other slices in the same way, by arranging the point cloud data of different slices, we can create the 3D model, point cloud, 3D point cloud. And this 3D point cloud we can use for the solid modeling, or we can for the STL part application or STL part processing. Here is another thing. Here it is the CT scan image. You can observe here it is the GIF image I have used, and I want to segment it out this part. So I have applied some operation in the MATLAB. If anybody is interested, then I can show you easy programming of the MATLAB to segment it out this part. So for the segmentation, I can use the threshold value, which is around the, in this case, that threshold value was around 100 or 100, 150. So on the basis of the threshold value, I have segmented out this bone and I have generated this 3D point cloud. And after generating this 3D point cloud, here you can observe this 3D point cloud. Here it is the one slice, and here it is the edge or the threshold value which I have applied. So on the basis of threshold value, I have detected the edge of this bone because I want to only generate the STL file for the 3D printing. So I not require the internal information. So that is why I have only acquired the edge of this femur bone. This is actually the CT scan of femur bone. Okay. And after that, this after applying the same operation for the different slices and number of slices, we can generate the STL file. Here you can observe the STL file. This STL file you can use for the 3D printing or the FEA analysis. Okay, and similarly, you can do this processes in any software like Mimics. I am showing here. This is the STL file, and here you can also see that example of tooth. So let me conclude first. And here these are the three parts of the tooth which we want to segment it out. So here it is the enamel, it is the dentine, it is the soft tissues or the pulp chamber or the root canal. We want to separate it out. So I have applied the different threshold values, and we have developed the different STL model of these three parts. Then I have assembled the three different parts. Then that part was meshed. So you can observe the density based meshing. Actually, we cannot uniformly mesh the tooth. Tooth will not have the uniform material density. So sometime we require to define the material property according to the material density for the ANSYS analysis or for the FEA analysis. So in this way, we can generate this mesh. That mesh we can assemble in any software or in any programming language you can also use. You can write your own program, and after assembly, you can, this is the entire step. After assembly, you can do the ANSYS analysis in your software, any software. So this is all about the data preparation for the FEA analysis. And if you have any question, then you can ask.
Hello, sir. I had a doubt. Yeah.
Yes.
So you showed the process of segmentation. So can you please tell me like which software you used for that segmentation? Like it was MATLAB or through Mimics you did it?
I have used Mimics. I have used the 3D slicer, and I have also used a customized program in the MATLAB for the segmentation or to develop the toolpath for the to develop the toolpath for 3D printing.
So when you exported your file from Mimics to ANSYS for FEA, so which file format you chose for? Because Mimics which I am using is not supporting for STL files. So is there any other way I can import that document in ANSYS? And also once I import that file in ANSYS, is there any way I can perform meshing, because it says it's not a solid form or it's not in homogeneous material, something like that. It was showing me that reason. So I wanted to know.
Yes,
like,
could you please repeat your question? In Mimics, you are not having the option to directly export this part on the ANSYS.
Yes.
So first thing, you have to have a thematic. It is another attachment with the Mimics. So first you require to export this part in the thematic. Then you require to do the meshing in thematic there and remeshing, fine meshing, whatever you want. And if you want to do the heterogeneous modeling for your FEA analysis, then you also require to define the material properties there only. Then after that, after defining the material properties, after doing the meshing, fine meshing, whatever you want, then you can export that model in the different forms, like the mesh format. I can say, I can't remember that exact extension, but you can easily export that FEA mesh directly into your ANSYS. you're not required to export the STL model into ANSYS, or you're not required to export the IGS model in ANSYS or any other software. You have to just export the mesh information, which is having the tetrahedral mesh or any other mesh. So that mesh you can directly export in the ANSYS.
Any question?
Hello?
Any more questions?
Yes.
Yeah.
So the meshing should not be done in ANSYS then. It should be done in 3-matic.
Yeah. 3-matic is more friendly for the human body part if you will compare it with ANSYS, because ANSYS will take much time, and it is not very easy to do the meshing of such free-form geometry in the ANSYS, because I have tried. However, I am not expert of the FEA analysis, but once I have tried, but or several times I have actually tried, but it was very difficult to do the meshing in the ANSYS for the free-form part, like a human body part especially. So for that, I would recommend that you should use 3-matic. It is the extension and of the mimics.
Okay. Thank you very much, sir. Thank you, sir.
Okay. Thank you, Dr. Nayak, for a very nice presentation about the application of modeling and simulation in the field of biomedical. So you have really give the glimpse of addition of engineering with the medical. So once again, I thank you very much. Thank you very much for the interacting session, sir.
Thank you, sir, for inviting me here in such a wonderful workshop.
Thank you, sir.
Thank you for entire organizing team.
Oh, welcome, sir. So now we will take a few short break, and again